Today we will learn the visitor pattern. This is the most difficult pattern among all the patterns that we study in this course. So please do pay attention for this lecture. Suppose that we have already designed and implemented a hierarchy of classes, such as those in the composite pattern. Recall that we use the composite pattern when the objects have part of relationship and also common operations. Now, after all these classes have been implemented, tested, and even already deployed, we discover that we need to add some new operations. There are many reasons to add new operations. For example, the clients or users may demand new functionalities. To add a new operation to a hierarchy of classes, the straightforward way is to insert the new operation into each class in the hierarchy. For this composite pattern example, we need to add this new operation to the base class component as a pre-virtual function, and this new operation to each leaf class and also each composite class. So what's the problem of this straightforward solution? Well, the problem is that we modify existing classes. In principle, we should always avoid modifying existing classes because they have already been implemented and tested. So modifying existing classes means that we have to test them all over again, and this modification process often introduces new bugs. What we want is to add new operations to a hierarchy of existing classes without modifying any of these existing classes. Is this really possible? We want to add new operations to these classes without modifying any of these classes. This sounds impossible. Let's take a look at real-life scenarios. Is it possible to add new functionalities to an organization without changing the existing structure of the organization? Actually, the answer is yes, by outsourcing. Let's look at one example. Suppose MSU wants to add a new functionality of room cleaning service. The straightforward solution is to hire some new employees to do room cleaning. To add these new employees, the structure of MSU has to change. For example, MSU has to add these new employees to their payroll systems, and MSU has to hire new managers to manage these employees, and the managers and these employees will form a new department, So, in other words, this solution needs to make changes to existing MSU system. Another solution is to outsource the room cleaning service to a company that specializes on room cleaning. Here we assume that MSU already has an office that deals with job outsourcing. Now let's consider software design. How to add new operations to some classes without changing any of these classes? The answer is the visitor pattern that we are going to study today. The basic idea is that when we design a hierarchy of classes, we embed a hook so that in the future, this hook can hook up with new operations. Just like when MSU was established, it has an office that deals with outsourcing. And this office can hook up with other companies with new functionalities. Therefore, when we want to add a new operation to existing classes, to avoid making changes to existing classes, we design a new class for the purpose of implementing this new operation. At the client side, we can hook up an object of an existing class and an object of this new class to implement the new operation on the object of the existing class. So here is the recipe for the visitor pattern. Because the visitor pattern is very complex, I give you a recipe and you should strictly follow this recipe. First, as we mentioned, for the existing class hierarchy, we need to embed hooks when we design these classes. These slides show how to embed hooks in the base class, we should always have a pure virtual function. This virtual void accept a visitor pointer and equal to 0. For each derived class, say x, add a function. We need to implement this pure virtual function. So we add a function virtual void accept visitor v, and then in this function, we have only one statement: v visit whatever this class is, say x, v visit the x, and this. Here, this is the address of the current object, say x. So in the circle class, here this means the address of the current circle object. And in the picture class, here this means the address of the current picture object. So why do we call this function hooks? This is because they can hook up with the visitors, right? So to let a visitor to do some job for you, here we visit circle this tells the visitor two things. First, I am a circle, right? First, tell the visitor I am a circle. Second, tell the visitor, here is my address. Here's my address. By telling the visitor that I am a circle, the visitor will know how to do the job for me, right? And by telling the visitor my address, the visitor will be able to find me and access the data members that he needs to finish the job. Now, when we want to add a new functionality, we design a new class that derives from the base class visitor. In the base class visitor, we have two pure virtual functions: virtual void visit circle, circles pointer equal to 0. And a second one is a virtual void visit picture, picture pointer with a picture pointer as the parameter and equal to 0. And in a derived class, for a new operation, we implement these two virtual functions. For example, suppose the new operation is printing. In the virtual void visit circle with a circle pointer, in this function, we implement the printing operation for the circle class. In this function, we implement the printing operation for the circle class. And here we have the circle pointer. We have the pointer to the circle. And in this virtual void visit picture, with the picture pointer as the parameter, we implement the printing operation for the picture class. Because the picture class is a composite class, which means that it has children. So we often need to go through all its children. We go through all its children and ask each child to accept the current print visitor. Here, this is the address of the current print visitor object. In this new class that derives from visitor, we may need to have a function called getVisitResult. Sometimes we need that. On the client side, we hook up an object of an existing class, such as this picture, this pic2, with an object of a visitor, say print a visitor object pv, by giving this pv as the parameter for the accept function of pic2. So pic2 accept this pv as the visitor. Now let's take a look of how does this is executed. Let's take a look. So this pic2 is a picture. Picture accept print visitor pointer, which means this function, right? So this is a print object, a print class that we have accept visitor, and in this function, as we said, only one statement. This print visitor v, print visitor v visit picture, and this is the picture object address. So which means that we will execute this visit picture with a picture pointer, right? With a picture pointer. And for all its children, now we see how many children this picture object has, right? This picture 2 has 4 children: a circle, a line, a picture, and a rectangle, right? So we are going to go through each of them. So the first one is a circle. Circle accept this. This is a print visitor. Circle accept this print visitor v. Then v visit circle this. V visit. This is a print visitor visit circle with a circle pointer. We basically call this function. All right. And for the second line object is the same, similar. And this picture, the third child is a picture, which means that this picture accept this. Picture accept this print visitor visit picture this, which means that we are executing this again. This function p visit visit picture with the picture pointer. This will be pick 1, right? So this means that when this picture object has one picture child, then this function, then this visit picture is called recursively. This is the UML diagram of the visit pattern. In the object class hierarchy, we call this the object class hierarchy, and we call this visitor class hierarchy. Okay, so in the object class hierarchy, we embed a hook accept visitor in each class. In the visitor class hierarchy, we have visit function for each concrete classes. For each concrete class in this object class hierarchy. Note that 2 things. One is the number of concrete visitor classes. The number of concrete visitor classes equal to the number of new operations you want to add to the object class hierarchy. This is one operation. This is another operation. So you can see that we use this class for the purpose of an operation. Second is the number of visit operations in each visitor. The number of visit operations in each visitor is equal to the number of concrete classes in the object class hierarchy, including both leaves and composites. So here we have 2 concrete classes, concrete element A, concrete element B. So we have 2 visit concrete element A, visit concrete element B. And if we have another class concrete element C, then we will have another function visit concrete element C. Applicability. So we use the visit pattern when we want to add new operations without changing existing classes. So here are some tips. First, for each class in the object class hierarchy, we need to add a hook for visitors, accept visitor with a visitor pointer as the parameter. And second, we need to provide methods to access the data members. This makes sense, right? If you want to outsource the cleaning jobs to janitors, you have to give them keys to your rooms, right? So second, we need to follow the principle thin concrete composite and fat concrete visitor. This is the principle that I come out with. So it means that, so in the accept function of a concrete composite class, don't put any other code other than visit concrete composite A. This. Always one statement. All right, so why? So first, you may want to change the way that you visit your children. And different visitor, concrete visitors may visit children in different ways. And there are many different ways. For example, if we traverse a tree, then you may have pre-order traversal, in-order traversal, and post-order traversal. So you should leave all these decisions for the visitors to make, not in the hooks. Because once you hook them up for the specific order, then all the visitors need to follow that order. So the visitor pattern example in the Gamma book did not follow this principle. So it's not recommended. And in the concrete visitor class, a stack may be useful for storing state information of the visit. We're going to see an example for that. And another tip is you will need forward declaration to break circular dependency. What does that mean? Now let's take a look. This is the object class hierarchy. So to compile graphics, circle, and picture, the compiler need to know visitor, right? Need to know the visitor class. So you need to have include the visitor.h, for example. Now let's take a look at the visitor class. To compile visitor class, you need to know, the compiler need to understand this is a circle and this is a picture. Now you see the circular dependency. To understand, to compile circle, the compiler need to know visitor. To compile visitor, the compiler need to know circle. That's why there's the circular dependency here. So in this visitor class, we can now say include circle.h and include picture.h. So we have to say class circle picture. That's it. This is called forward declaration, which means that, so we are basically telling the compiler, say, hold on, this is a circle class. It is a class. Later you will know what is the circle class is, how it is defined. But to compile right now, you just know this is a circle class. And similar, this is a picture class. And also you need to read the Gamma book visitor chapter. Now let's take a look at an example. Suppose we want to design classes for representing a tree. And here, for the tree, we have two types of nodes. We have terminal nodes and non-terminal nodes, and then terminal nodes have some children of either terminal nodes or non-terminal nodes. So of course, we use the composite pattern. Now we need to design a visitor forge for this tree. For example, we can calculate the sum. Suppose each terminal node has some values, and each non-terminal node does not have no values. That's our assumption. We have two implementations of a concrete visitor. One is stack-based, another is non-stack-based. Now let's take a look of how this is the stack-based implementation. So we have a stack, right? Suppose this is integer, and for one, remember there are two types of concrete classes: terminal nodes, based on non-terminal nodes. So then we have two functions, right? Visit terminal nodes and visit non-terminal nodes. And also we may have a function to get the results, right? And to implement the terminal nodes, the parameter is the terminal node pointer. We basically get the value from this terminal node pointer and push to the stack. And to visit non-terminal nodes, we have a non-terminal node pointer. We basically to get the non-terminal nodes, how many children it has, we have a for loop. And then to get its ith children, to get its ith child, and ask each child accept this concrete visitor. Right? Accept this concrete visitor. Now after this loop, so the top of the stack, and suppose this this node has say 10 children, and then the top of 10 elements in the stack are the results of the traversal of its 10 children. So to calculate the sum, we initialize sum equal to 0, and then we go through this loop of how for all the children, we basically get the top from the stack, and add to the sum, and then pop it out. After we pop the results of all the children out, and then we replace it by the sum. By sum, we push sum to the stack. After the whole tree is done, is traversed, the stack should have only one element, which is the sum. We basically get the top from the stack and give it to the result, and also pop this out, and then we return the result. Note that we have to pop this out. We have to clean up the stack because we want to avoid side effect of one round of visit on another round of visit. This is the non-stack implementation of the concurrent visitor. So here we don't have a stack, we just have a sum. And in the constructor, we assign 0 to the sum. We initialize it to 0. And of course, we have two functions, visit terminal node, visit net terminal node, and we have another function, get the result. And to visit terminals, we basically get the value from this terminal node pointer, get the value, and then add to the sum. And for non-terminal node, we have a non-terminal node pointer. We basically go through all its children and ask each of them accept this concrete visitor as the visitor. And during this process, so everything, all the terminal nodes of this non-terminal node are added to this value sum. Okay, and then to get the result, we basically assign sum to result and assign 0 to sum and then return the result. And here again, sum equal to 0 is to avoid side effect of one round of visit to another round of visit. We want to avoid such a side effect.